And we're live. Hello, everyone. Welcome to our live Ask Me Anything session with a team that brought to you Hugging Face audio course. So today we are happy to answer your questions about audio, about the course. If you have already tried to practice your skills and have encountered any issues or have any questions, go ahead, drop them in the YouTube chat. And I'm going to start by introducing the team. So today we have Sanchit, who is a machine learning engineer for audio in the open source team at Hugging Face. We have VB, who is a machine learning developer advocate at Hugging Face, focusing on audio primarily. We have Matthijs, who is also a machine learning engineer for audio and also author of a book on how to write sound synthesizers. And he also creates plugins in his spare time. And I'm joining as well. I have been leading this project to bring this course to you. And today we are going to be talking, well, not talking, we're going to be listening to you, to your questions, and then trying to answer them to the best of our abilities. Before we get to the questions, I want to pass the mic to VB, and he's going to say a few words about the course in case you haven't started yet and you are wondering what to expect. Go ahead. I'm going to add your slides.
Perfect. Can you see my screen? Or is my screen up?
Yes, we can.
Okay, perfect. All right. Good morning, afternoon, and evening from wherever you all are joining us from. I'm just going to take a quick, maybe like a minute or two, and just like walk us through like what exactly do we cover in the course so far. So at a 10,000 feet, like the Hugging Face audio course essentially like walks you from, what can you do from an audio and like, what all kind of downstream tasks can you perform with it, right? So this involves doing classification, this involves, doing speech recognition, and, later on we'll be covering certain things like text to speech and, other audio related tasks. The course in itself like expects very little background. So essentially, we start off with understanding what exactly audio is, like what is an audio waveform comprising of, how can you represent it, and how do you work with it, what are certain libraries that you can use, and so on, right? So the first unit essentially covers that, like how do you load an audio, how do you pre-process it, how do you stream it, and we have certain quizzes and certain readings that you can go along with the course, with each unit to test how much you know about this specific unit. And so we start off with like how do you work with audio data. Then then the unit 2 is essentially, as soon as you understand what exactly is audio, then we look into certain applications of it. So for example, how can you classify audio, how can you use the Hugging Face ecosystem to essentially use pipelines, which is our abstraction on certain specific use cases, like classification, speech recognition, and extracting embeddings and so on. Like how do you essentially use all of those? And then we move over to what kind of architectures for audio exist. So we go through what exactly is a transformer type model, and just essentially provide like a refresher on it, what kind of architectures are typically used in audio. And that's like up until unit 3, we essentially work on the foundations that you need to know for you to be able to maximize audio use cases and like essentially understand everything else from it. And then unit 4 and 5, unit 4 essentially covers how do you build an audio classification pipeline, and we have a fantastic sort of music genre classifier that we go through. And at the end of both unit 4 and unit 5, you essentially have your own sort of fine-tuned model for a specific task. So you go through like code as well as like understanding for building such use cases. Yes, and just to wrap it up, Unit 5, which is something that we released yesterday, is on speech recognition, wherein we cover like how do you use models like Whisper to create your own speech recognition pipelines. Right, and many more to come. So we're going to release the Unit 6 next Wednesday, and so on. So stay tuned for that. Ooh. Happy to take any questions on that.
Thank you for this overview. I think we can start with the questions that we already received on Discord. The community has already started a thread with questions, and let me just bring it up to see what is there. The first question that we had was whether we have any plans in the long term to add more cool courses or expand the current ones. Excellent question. We have lots of ideas for courses that we could potentially do. So there's some modalities that we haven't covered yet. There's some advanced topics related to production, performance improvements, and things like that that we haven't really touched on. There's also, of course, the other end of the spectrum, the foundational topics that we normally don't cover because we usually cover more advanced topics. We expect people to understand the foundations of deep learning, machine learning. However, whether we're going to add any of the courses really depends on a lot of factors. Adding new courses is usually a lot of work, and it involves multiple team members. And we have to carefully consider whether we want to prioritize creating this kind of educational content on top of already existing documentation and notebooks and examples that we have, or whether we need to prioritize other projects. And so I cannot give you a definitive answer, unfortunately, whether we're going to have the courses. We certainly would like to, but at the beginning of every project that we are considering to start, we are evaluating the priorities and then reevaluating them again. So when we get to the point that we're considering another course, then that's when we're going to decide whether we're going to have it. But we do have lots of ideas of what we could do. And so sorry that I can't give you a definitive answer on that, but we're definitely considering more courses. I hope this answers the question to an extent. And then with that, I'm going to go to the next question, which was, I work with neural time series data, EEG and fMRI, which are technically very close to audio signals. And I'm interested in using transformers for this type of data. Do you know of any applications of transformers in analysis of neural time series data? In my experience, neuroscience lacks usage of advanced ML models, and it would have been very beneficial for the field if you had a course on that or an extension to this audio course where neural time series data were used as an example. I wonder if somebody from the team would like to answer this question.
No, I think it's a very valid question. I think what you said about the similarity between audio data and any kind of time series data holds. So I think the way to view the audio course is to think about mapping from like a time series domain to another domain. And so you're doing this sequence to sequence mapping. And you can use the audio course as a way of learning the fundamentals there. And then it's kind of agnostic to whether you change that input and your output. So if you change what you're mapping from and to, it doesn't necessarily change the modeling part. The model is kind of agnostic to that. In the same way that a lot of what we cover here is actually very similar to computer vision. Like we've spoken a lot about MEL spectrograms, which are basically images. So a lot of what we're doing is actually just like an image classification problem or image to sequence problem. So I think the audio course gives you like a nice fundamental understanding for how to maybe apply these models in a different field. regarding neuroscience, my experience of this little experience I've had in the field of computational neuroscience, there's a lot more emphasis placed on understanding and interpretability of models. So the whole point of one is that a big endeavor in neuroscience is trying to understand how the brain works. And these machine learning models might emulate tasks that the brain does, but it's very hard to understand how they work. And so interpretability remains quite low, which personally is one reason I think advanced ML techniques are not applied in the same way to neuroscience that they are, say, speech recognition. We don't need to necessarily know how the brain works to transcribe speech. But if you're doing neuroscience, probably you do need an understanding of how those models work, which is why you favor simple linear architectures or models that you can probe and look specifically at the weights and the layers and the convolutions and try and understand what the model's doing.
If I may add something to this, there was a recent post on Hugging Face's blog exploring Autoformer, which is a transformer architecture for time series. And I know that there are two more, or maybe even more than two, at least two more transformers for time series that Hugging Face supports. One is even called time series transformer, and the other one, unfortunately, I forgot in the moment what it's called. But there are several transformers specifically for time series, and the recent blog post explores efficiency of Autoformer for this kind of applications. And I think it's worth looking into and exploring them as well, in addition to audio transformers, for example.
I'd like to add something as well, because there's something you have to be careful about if you're using an audio model for something that's not audio, because sometimes these models make certain assumptions about the data. So for example, a MEL spectrogram might not make sense unless you're actually dealing with audio, because the transform from spectrogram to MEL is based on the human perception of sound, which it wouldn't make sense if you use that on other data that's not audio. So that's something to be careful about. So you might not be able to just take an existing audio model and use it with different data. You would have to make sure that any transforms that happen inside the model, any pre-processing, still make sense for your data.
Absolutely makes sense. The model designed for specific modalities usually have some expectations for what the input is. And I think with that, we can move on to the next question. And the next question is, what are the current challenges of audio machine learning, and what is the most exciting SOTA, state of the art, in this field right now? Anybody wants to take?
It's tricky to get consensus on that now, because every paper says I am the current state of the art. But maybe I can quickly talk about text to speech, and then Sanchit or Matthijs, if you want, we can talk about like speech recognition and so on. But quickly about text to speech, in terms of like the current state of the art. In terms of closed source systems, we have this sort of new breed of models, which is taking a text and taking instead of using spectrograms as a representation or just directly modeling waveforms, we model semantic tokens of the waveforms and essentially do like language modeling style learning as we do in text for audio. And Bark is a very good example of it. Music Gen is also a very good example of it. And these type of techniques are now like more and more models are adopting these, right? And that's pretty much like where the sort of industry where industry and academia for text to speech is moving. So now you don't see like as much as fast, so more like tacotron or autoregressive types like previous models which were conditioned on MEL spectrograms and so on. Just in terms of like purely in terms of numbers, the Natural Speech 2 paper by Microsoft actually claimed that in terms of pure mean opinion scores, which is a measure of how good the quality of the audio is, they surpassed human level evaluation. Again, like there's more to sort of read into it, but that's just to give you an understanding of that we're very, very close to mimicking audios and so on. And you can see that with startups by the likes of 11 Labs, Play HD, and so on, that they're able to have really high quality speech, which is often indistinguishable, and so on. So, yeah.
I guess regarding speech recognition, we kind of had like a big wave in the last couple of years. So first, Wave to Vec 2 really opened the doors for pre-training fine-tuning. So if you come across BERT or GPT-2, it's the same paradigms that really led to the explosion in NLP. We saw that for the first time a few years ago with Wave to Vec 2, and then Whisper was an advancement and a step forward based on that. And so it's definitely a case that it's a very exciting time in audio in general. We're seeing that big boom in models that we saw a few years ago in NLP, and lots of breakthroughs and advancements. And speech recognition is probably a little bit ahead of text-to-speech in that regard. Like model maturity is a bit higher. We see a ton of new text-to-speech models come out every week. With ASR, there's pretty good consensus that Whisper is the best open source speech recognition model available. But there are still new models coming out, like MMS, which came out a few weeks ago by Meta, and it's a development on Wave to Vec 2, and it's better in some cases for very low resource languages. And yeah, I guess we're seeing also the field of now just general text to audio generation. So it all uses exactly the same things that Vivi mentioned with text to speech, but you just generalize. Instead of generating speech, you can generate any audio, so music, sounds, whatever.
I also think that there are challenges with stuff like text to audio or text to speech, in that text it doesn't have a lot of information, or it misses certain information, right? So if you have a sentence, you can read the sentence in many different ways, and it's tricky to model this just from text. So I think we'll see more work done in that area. As for like music generation, I think one of the big problems is that generation of images works very well, as we've seen over the last year or two. These models make absolutely beautiful pictures, but the music generation models, they don't make very convincing music just yet. They've been getting better, but maybe the problem with making music is that our eyes tend to fill in things for us. So pictures, it's easier to make a picture that looks convincing than just to make music that sounds convincing. There can be many little details wrong in the sound, and we won't like it. And I think maybe that's one of the challenges for music generation models, is that it's a little bit harder to create music that sounds convincing than it is to make pictures that look convincing. But maybe we'll see some interesting developments of this, or interesting improvements. People have been putting more effort into the graphics and image side of things than into the audio side of things. So as more attention goes into the audio, into audio generative models, maybe we'll see some great advancements there. It's interesting times.
I like that you touched on music in your comments, because our next question, so it nicely segues into our next question, which is, for me, I'm not interested in music. What are other applications or cool things for audio I can build? Can you give me some examples that are helpful or cool? What things to keep in mind when trying to build a model for mobile applications for voices? And on top of that, there's another question about visualizing in 3D. But I think we can split it. Let's keep first the part with the examples which are not music. And I think we've touched a little bit on speech, but maybe beyond speech and music, can you think of other applications? I can mention one that I personally really enjoy. And there's probably more than one, but there's this app that recognizes bird sounds, and I can identify birds in your area. So I personally enjoy using that a lot. And I know that in conservation projects, studying, identifying animal species can be used with audio, but there are obviously many more applications. Sound is everywhere around us. So what are some cool applications that you can think of?
I guess the cool thing about what we've done in Unit 4, if you've read the audio classification chapter, then the application Maria just described of classifying bird sounds, you could theoretically do with the fine-tuning script and the knowledge that you've obtained. You just have to swap out the dataset from a music dataset to one where you've got birds and the labels. Instead of classifying what kind of music genre, they're the bird sounds. So like it's kind of, yeah, I think so far audio classification in particular is kind of categorized into 3 subgenres. We see mainly speech music and sounds, like sound classification. But this is just like one piece in like in a bigger pipeline. So I think if you're like interested in speech, you can think about all the little components that you can put together to maybe build your own like voice assistant. So you have audio classification to recognize a wake word, and then speech recognition to transcribe what you're saying, and then text to speech when the voice assistant replies. And all of this, like every stage in that process, is an audio application. They're just different tasks within the audio domain. But yeah, there are loads of exciting, just even sound classification tasks as well.
So one application of this, it's a type of classification, but it's more like the domain of anomaly detection. So you can have little microcontrollers, for example, listen to the sounds your machines make in your factory. And when they suddenly start making different sounds, obviously something's wrong with the machine. And it's kind of an easy way to detect if something goes wrong in your factory, even if you don't have sensors on those machines, for example, because everything makes sounds. And if the sound's suddenly different, that might be cause for an alarm. So that's one thing that's actually being used in the industry.
I remembered another application for audio sound, audio classification, which probably can come as a surprising application. And there were some researchers that studied the sounds that tomato plants make when they are in distress, lack of water, other kinds of stressors. We don't hear those sounds because they're at a frequency that we don't register really, but something's happening, like maybe cells are popping because of lack of water, that they can record actually, and they can classify based on different stressors. So even if you cannot really hear the sound, that doesn't mean that you cannot apply audio approach to it. Just have to be, I guess, creative in how you approach a problem. So there's another unexpected probably example of using audio.
Yeah, and I mean, just one quick sort of example which I just remembered is that you can, so even though like you don't want to deal with say music, like there's like an entire field of music transcription. So like converting sort of proper music and like all like removing the acoustics and just focusing on the vocals and like getting the transcription of that is like something which is like a field which is popping right now. And then of course, as Sanchit mentioned, there was this entire sort of like there is classification, then there's like of course text to speech like on device, and then also things like voice conversion. So just adding like filters that you see on Snapchat or Instagram on your voice is also something that you can do on device using quantized models. We do have some of those on the hub, so search around and definitely play around with those.
Thank you. I see a question on the YouTube chat about who's choosing the questions, and I want to clarify that we're going first for the questions that we have received on Discord, and then we're going to switch to the questions from YouTube. I think We'll have plenty of time for all of it. So don't worry, we'll get to your questions. And so let's just continue with the next one. Whether we have a guide to fine-tune transformers on another language. I think this is a very quick question to answer. Sanchit, do you want to take this one?
Yeah, check out Unit 5. That's your guide.
Yep, that is exactly what you're looking for. So this is covered in great detail in Unit 5, and so we can jump to the next question. Can you please share best-known practices for fine-tuning pre-trained Hugging Face models? What are the recommended practices to debug loss metrics and do hyperparameter tuning? Specifically, what are techniques to avoid overfitting? I think maybe we can try to answer this question briefly because it's not exactly related to audio, but still it would be nice to give like a couple of helpful tips. Who wants to take it?
You go. All right. So like so it's half science, half art training machine learning models. And so you have to fundamentally understand what you're trying to do. And your objective is to maximize / minimize your evaluation metric. And you do this through a proxy metric, which is your loss. So your training loss, you want to go down over the course of training. And the art of looking at a loss curve and knowing, yes, is this going in the right direction? Am I starting to overfit? Have I set the learning rate right? Have I set the batch size right? You can only really get through experience. There's not really a hard and fast rule that you can apply to every system. Like I know from fine-tuning CTC systems that they intrinsically have a different loss curve from sec to sec ones like Whisper, and I look for different things when I'm debugging. And there's not necessarily like something that covers everything, but there is a really nice playbook by Google that they released a few months ago, and this kind of gives you the most important knobs and dials that you probably want to play with. So there's a batch size, learning rate, dropout, and your learning rate schedule, like how long do you want to train for? And so these are the things that you probably want to start looking at. And so I'll send a link for that in the chat. Maybe we can also learn.
Yeah, I mean, I was just... Okay, so just one quick thing. Yeah, I was just gonna say that, you know, like in general, like for all of these things, it's very important to, you know, like sort of essentially like look through and like record as much as you can. So if you're using like you know, the Hugging Face stack, like make sure to like set WANDB to true, so that like you can record all the logs in like in WANDB and like essentially like compare between your different runs, right? And a good idea is to essentially like you know, isolate your sort of training data and then like loop like go through different parameters and then like see like what sort of influences your output much. And like, you know, you can also sort of like look at certain predictions whilst the model's training as well. So, you know, in general, like I would recommend just like recording you know, as much as you can and like logging as much as you can, so that like you have a more holistic idea of how your training runs are going and compare them later on.
Yeah, all I wanted to add to this is that the question asked best known practices for fine-tuning Hugging Face models. It doesn't really matter if the model is Hugging Face or not. All these things, they work the same way. So you could use the Hugging Face, the trainer or the accelerate library to train the model. You could also use some other library like PyTorch Lightning, or write your own training loop, whatever you're comfortable with and whatever makes sense for you. All these different pieces, they can all interoperate together and work together. So it doesn't really matter. You don't have to use the Hugging Face trainer, for example, although it's quite convenient and it's probably a good place to start.
Thank you. So we're gonna have 2 more questions from Discord, and then we're gonna switch to the questions from the YouTube chat. One question which I think is also going to be pretty straightforward to answer, hopefully. Whisper does a good job transcribing general conversation, but when having a domain-specific speech, it fails to recognize some words. What would you recommend to deal with new entities and words?
Matthijs, do you want to? I think you've.
Yeah, so one way to do this is to use prompting, which is a feature that was added not too long ago to the Hugging Face version of Whisper. And prompting lets you add context to the thing that's being transcribed. And it's not a perfect solution, but it sort of primes Whisper to understand different terms, different words. That's really the simplest way to do it. You would have to experiment with it to see if it works for you or not.
And probably the longer and more expensive and more time-consuming approach would be to gather a domain-specific data set to fine-tune. But yeah, if you're looking for a quick solution, this what Matthijs suggests looks like a great starting point.
Yeah, and the idea behind Whisper was kind of that you don't really need to fine-tune it. Like, it already knows a lot of stuff. So it's nice if you don't have to fine-tune it and you can get away with the prompting. But yeah, it's always possible to fine-tune if you have the data.
Absolutely. And a final question from Discord, and before we switch to YouTube questions. Just a second. And this question is about recommendations for people who are low on computing resources. So no GPU at home or free collab tier exhausted. What are the recommendations for the most cost-effective way to experiment, like fine-tuning pre-trained models with a reasonable budget? I can give a few quick tips on that. So if you go to Hugging Face docs, if you go to Transformer docs, so there's a whole section on performance and scalability, and there it contains a lot of information on how the model consumes memory during training versus during inference, and what are the knobs that you can turn to improve, to optimize memory usage, to increase speed of training. So you have tools like gradient checkpointing, you have tools like gradient accumulation, you have mixed precision training. You can combine all kinds of different techniques to make the training more efficient, and optimize the memory usage. And that would be a good place to start, I think, although it is a bit advanced.
Yeah, I think also like you can pretty much use things like Kaggle notebooks. You will need to create a Kaggle account. So that basically serves as like a drop-in replacement for Colab. You have limited sort of GPU hours. So I think it's limited to something like 20 GPU hours per week, but that should effectively breeze you through the speech recognition as well as the speech classification, the audio classification task for sure. I think that would be like the most easiest way to like go from like a Colab like setup to like a Kaggle notebook style setup. In case like you're looking for the most cheapest option in terms of GPUs, I think Paperspace provides like student discounts and like also like academic discounts in case like you belong to those groups. Then you can apply for those. But yeah, hope that helps.
Yeah, I also use Paperspace for my own projects, spare time things. It's pretty inexpensive. It's a lot cheaper than buying your own GPU or doing something on like Google Cloud. It's worth looking at which of these services offer the best resources. If you're really strapped for resources, my main suggestion would be to use smaller models, because that's that makes the biggest difference.
Absolutely. Let's switch to the questions that we've had on YouTube. Starting from the very beginning. are we going to have a section in the course on music generation? I'm working on a project that uses ControlNet and MusicGen, but I want to know how I can use these. So I probably can answer this. At the moment, we do not have music generation in the curriculum, but we are considering possibly adding it. So we don't want to commit to it right now, but we might add it to the course as a bonus.
So we have two, well, as of 1 hour ago, we have 2 models for music generation in transformers and one in a couple in diffusers. And so it could be something that for sure we kind of do like a hands-on with all of these. But it's a pretty exciting space at the moment because it's, like there's so much attention in music gen. So we can try and write something that keeps up with what's going on.
Yes. There have been several questions about transcription, specifically real-time transcription, sorry, and whether you can do this with Whisper, transcribe speech in real time.
Yes, you can. I'm just trying to find the GitHub gist that I had, but essentially, like all you need to do is just create like a microphone object and pass it through the pipeline, and you can do it via. I'm just pasting the link on the chat, and it just works automatically with the pipeline. Of course, it assumes that you're running like locally on a GPU. On a CPU, it's really slow, specifically for Whisper. But yeah, you can essentially use the same sort of same code that I've linked and like swap that. Like instead of the OpenAI Whisper-based model, you can swap it with Wave2Wake2, and it should give you a more sort of streamlined performance on CPU, or like more faster performance on CPU than Whisper.
So the thing to remember with Whisper is that it's sequence to sequence. So you have to wait till all of your input audio is ready before you put it through the encoder, and then you generate one token at a time. So actually what VB is going to show in a second is it's kind of like a trick to getting past this bottleneck of waiting for all of your audio, where you wait for a little bit of your audio, a predefined amount, and then as soon as you have that, you put it through the model and it starts generating, and then you wait for the next bit, and then you start generating, and then you're going to have a boundary in between the two, which is where you have to stitch the 2 chunks together. So this is kind of like a workaround to make a model that doesn't work real time work semi-real time. So you have to like define how real time you want it. And so the more real time you make Whisper, the larger the performance degradation. The closer you go to offline, where you wait for all of your audio, the better the performance generally is. So this is something you have to also trade off. Like how much do you value the model working real time versus having good word error rate accuracy?
And for Whisper, it's actually not that it needs all the audio, because it works in 30-second chunks. So that's like, if you wanted to not use this trick, then your latency would always be 30 seconds, right? And this trick, I think it makes it use smaller chunks each time. So you can reduce the latency, but your compute goes up.
Yeah. Next question. In light of the conclusions made in Hugging Face Ethics and Society newsletter number 4, despite it being focused on text-to-image models, do you plan to encourage considering ethics during model development? So in the unit that is dedicated to text-to-speech that's coming soon, we definitely mention ethical considerations of developing such models, and as well as in the docs for this model and on the blog, when we wrote about this model, we mentioned ethical consideration because obviously there's a lot of potential malicious use for text-to-speech models. And thank you for bringing this up. Absolutely. You should be training and using these models responsibly with understanding the consent of the data being used, consent of the people's voices that are being used, how they're going to be used. Absolutely. This has to be considered. Do you create content using Hugging Face models? Yes, models that we use in the course, they are all available through transformers. And we all use Hugging Face transformers and Hub and Hugging Face datasets, which are all available for you, open source and free. Next question.
Yeah, just wanted to.
Oh,
Yeah,
sorry.
go ahead.
No, I just wanted to like quickly say one quick thing. Like whatever you learn in the course is not like I mean, of course, like we use Hugging Face stack to like showcase like how exactly do you do X, Y, or Z, tasks. But you can pretty much like use the same concepts and do it without the Hugging Face stack as well, right? So like you can pretty much use like any open source implementation, and there are plenty. If you look out, you can also like sort of use those. So I just don't want people to feel that they're sort of marrying into like a ecosystem, but you're essentially like the course focuses on like the foundations and like how you can do X, Y, and Z things and like tasks.
Yeah, I took this question, do you create content using the models, to mean like that we use like GPT to write the course, but we wrote it all by hand. It's all human generated.
Human generated, human reviewed. In that sense, yes. You're right. This question can be understood in several ways. Let me check what other questions we have. What is the next one? Give me a second. What do you think about developing objective quality metrics for text-to-speech, as MOS depends on the setting of the experiment and could have some biases? This is a very good question, I think, because it is challenging to objectively evaluate TTS models. I think we're going to talk about this in the unit that is coming soon, but perhaps we could discuss this now as well a little bit too.
Right, I can probably take a stab at this. So like typically, like if you look at a text-to-speech model, it's supposed to do like two things. One, it's supposed to generate like an audio which you can understand, and second, it needs to be able to sort of pronounce different phonemes in the right way, right? So of course, like the sort of industry standard way of doing this is through a mean opinion score, wherein like you have like 4 or 5 audio samples, and you call upon say 100 to 200 sort of people from diverse backgrounds and have them listen to your audio files and give it a score between 0 to 5, right? So 5 being very good, 0 being that they cannot understand it at all, and then you average those scores and then you get a MOS score, right? However, that in practice is not really feasible, and involves a lot of time and effort just in general. So what we like, there are certain proxy metrics that you can use, right? So like one thing that you can definitely use is like something like some sort of like objective metrics, like signal to noise ratio in the output of your speech, like how much is the noise versus like how much is like speech in the in whatever audio file that you have. There are also like certain sort of metrics like STOI. I keep forgetting the full form of it, but it is essentially something that you use for like telecom providers use to test like how, like what's the perceptual quality of your audio, right? So you can use those metrics, which give you like a de facto standard sort of like number of how's the perceptual quality of your audio, and of course like you use some sort of ground truth. So like you for example, when you train a text-to-speech model, you would have certain speaker. So in this case, the speaker can be me. And then the way I say, that could be the reference audio. And then we train the text-to-speech model to mimic me, right? And then we compare how I speak with how the text-to-speech model generates certain phrases. So that way, like, you have a reference and you have like the generated audio, and then you can compare them, and you can use like pretty much all sorts of simple, objective metrics. Last but not the least, there are like certain MOS models. So like MOS architectures. So you have wave 2 based MOS architectures, and so these are like models which were trained to essentially give a score between 0 to 5 for a given audio. Of course, a lot of them are for English, but there are like some for other languages, and you can use those models as a proxy for a MOS survey as well. So yeah, it's like evaluating text to speech is like a topic which like everyone fights about, and there's no consensus on it. But essentially, like, what you try to do is you try to get very close to reference audio, and then use certain objective metrics to get there. More on that in the unit 6, I think. But yeah.
All right. Anybody wants to add anything? No. Okay. Moving on. There's a question about vector databases. So just the way how embeddings for NLP models can be stored in vector DBs, is there a similar approach for audio?
So yes. So like we have models like CLAP. I keep forgetting the full form of CLAP, but it's similar to clip for image, right? So essentially, like, you give an audio and you get some sort of embedding out. Like, embedding is essentially like a numerical representation of, or like a condensed numerical representation of an input. Like in this case would be the audio waveform. And so in practicality, you can essentially pass all of your audio files through CLAP and get some sort of representation out of it, and then like use those and like save those in like your vector DB and so on. There are other models for this on the hub as well. So you can also use wave 2 to generate like representation of your audio files, like essentially embeddings. And you can also use encodec, which is like one of the more recent addition to the library. We merged it last week, and like plenty more. I'm also sure like you can use Whisper and just get like the encoder hidden output for that as well. So yeah, long story short, you can save it. You just need to find which architecture works best for you and for your specific task, and it should work the same way as it works for text.
Thank you. There's another question about generating audio and how to set an emotion for the output. How is this approached?
I can take that if you want. I'm like, so just in general, like text to speech is like a thing which I like research at the moment, and like have been doing so for the past 2 years, and that's just something which I'm really passionate about. But okay, so let's think step by step about this. Specifically, for you to generate emotion in an audio, you need 2 things. You need some sort of like guidance to the model to know that, hey, like, you want to generate this audio in a more sort of angry voice, or in a more sad sort of voice, and in a more sort of happy voice, and so on. So what we typically do is we model these emotions in, like, of course, in latent space. We are another like subcomponent of the text to speech pipeline. So think of it this way, that you have like the input, which is text during training. Then you have like reference audio, which we use to generate, and alongside that we create a sub network whose sole task is to model the emotion. This you can do with speaker embeddings, as we were saying before, because speaker embeddings or like any embedding for that audio would also model some sort of variation in the in the audio as well. So these variations are known as, we typically call these as prosodic features. So prosody is like how you say. So I can say, I can say, or I can say, different ways of saying say. So essentially, like you take a model and you model these sort of variations with that model, and the embeddings actually capture it. And through time and like through a lot of training data, so through like 10,000s or like potentially hundreds of thousands of examples, you learn these variations, and then you effectively get to a point wherein you can tweak these and then like add emotion, so to speak, to the generated audio. Like in case anyone wants certain pointers, like what you want to look for is Tacotron 2 and GST. Like just search these two things. That was the first time that we were like effectively able to model emotion for text-to-speech systems. And yeah, you can read more about it, or just like tag me on Discord and we can have a longer chat about it.
I've also seen systems where the input text is they add annotations to the text. So Bark, for example, does this, where you can add specific like keywords like screaming or something, and then the text will be screamed at you. Yeah, so that's another method of doing it. I think some commercial systems also allow you to add additional information to your text, such as like the speed with words are spoken, the pitch, and so on. So these would be additional inputs going into the model. But then, of course, you also need to train the model with such data. So it's already difficult enough to get enough training data, just text to speech, like good training data. So having data with additional information about the prosody and the intonation and stuff, that's just that gets expensive really fast, I think.
Yes. I'm gonna turn attention back to Sanchit now, because there's a question right for you. When you fine-tune a model like Whisper on a language which wasn't the original model, in the original model's data set, what happens with the tokenizers?
Okay, so there are two things that we can do in this situation. The first thing is that we can do what we do in the hands-on, or sorry, in the fine-tuning example in Unit 5, where we pick the language in the tokenizer that is closest to the new language that we're fine-tuning on. So in the example that we give, we want to fine-tune on Devehi, and that the Whisper model has never seen this language before. And so what you have to do in this circumstance is do a bit of linguistic detective work. So what I did was I Wikipedia'd the Devehi language, and I looked at which language was most linguistically similar. And I saw that it was the Sinhalese language. And I checked this language, and it was in the Whisper tokenizer. And so Whisper has seen this language during pre-training. And the reason that we give this language then to the tokenizer during pre-training is that we want to have Whisper use the knowledge that it has about Sinhalese and leverage that for the new language that it's not seen before. So it knows suppose like you know French, and you want to learn a new language. Probably the one that's most linguistically similar is Spanish. So like if you take a French speaker and then they learn Spanish, it's going to be quite similar in terms of vocabulary. We do the same here. So Whisper already knows a bit about Sinhalese, and so now we tell it like Devehi is quite similar to Sinhalese, so you should use this knowledge on the new language. So that's what we do in the notebook. And as you use your fine-tuned Whisper model, you should, instead of like when you specify the language argument, you can just specify this as Sinhalese. Then in the future, like when it's fine-tuned on Devehi in this way, it will treat Devehi and Sinhalese in the same way. And the other way, which we've also tried and pretty much gets similar results, is that you just don't tell Whisper what language it is and tell it not to predict the language. And so then it stops making the language prediction. And And we found that they're both quite similar, but we found, there's like marginal performance gain if you do this like language tricking idea. So it's the one that we went for. Hope that explains.
And so, like the Whisper tokenizer, it has like 50,000 tokens in it already. So it already covers a lot of possible combinations of characters and words, parts of words. If you want to like replace the tokenizer with your own specific tokenizer, that's probably not ideal, because that also changes the size of the tokenizer, and it changes the size of the embedding. So you'll be throwing a lot of information away that Whisper has already learned, right? So what Sanchit suggested about try to reuse existing languages and the existing tokenizer is probably the smart approach for Whisper. For other models, you might actually want to create a new tokenizer specifically for your language. I don't think it makes a lot of sense for Whisper. I don't know if, I hope I'm not lying here, Sanchit. So.
No, I think that's exactly right. And the first thing you can check is just make sure that your vocabulary is in the Whisper tokenizer already. So just encode a sentence and decode it. If you get the same thing out that you put in, then Whisper already has these characters, and then you don't have to worry about any of this tokenizer reshaping. If you don't have the tokenizers in the vocabulary already, Whisper might not be such a good model to fine tune. In this case, you might be better doing something CTC based, purely because it's just easier to build a CTC tokenizer. And we can share like a blog post for doing this with the new Meta MMS models.
All right, we have about 4 minutes left. There was a question about essentially audio to audio models, which we haven't touched on today yet. And how would you essentially translate speech in one language to another language, to speech in another language?
And I think the basic nuts and bolts are there, right? Like at the end of the day, if we're doing, for example, speech to text, we're going from speech, and then like, so let's assume like a encoder decoder model. So where we're encoding speech and then we're decoding in text, right? So you can pretty much use the same basic principle, and you basically encode speech and then you decode in like speech in other languages, and like you can then like define certain controlling parameters to do that. But the basic principle throughout remains the same, that you essentially like take an architecture which goes from like one sequence to the other, and then sort of model it or well, train it that way. And like, of course, like you'll have to make like certain changes here and there, but by and large, the task remains the same.
Yeah, and we have one example in Transformers. I think at least one anyway. In Speech T5, it has a voice conversion pre-trained model, and Speech T5 has been trained on text going in, speech going out, speech going in, text going out, and speech to speech. So they trained this on all the various combinations. If you have the input sequence is text and the output sequence is speech, then there's like a difference between the lengths of the sequences that the model needs to deal with. When you have audio going in and audio going out, these sequences are a bit better matched. So in that sense, it might be a slightly easier problem for the model to handle. But yeah, like VB said, it's if you have a sequence-to-sequence model, you've got one sequence going in, one sequence going out, and basically what you need is the right data to train it. And yeah, if you're interested, check out the Speech T5 voice conversion model that we have.
Do you think the recent model by Meta AI, the MMS, massively multilingual speech, I think it's it is abbreviated from, do you think you could use this one for audio to audio task? Specifically for translations, as it is the model that supports a lot of languages.
No, so this is a model that fundamentally uses the CTC decoding algorithm, and so it's just an encoder model. And so like I would encourage you to check out Unit 3 on audio architectures. And so the problem with using MMS is that you're going to put a sequence of audio inputs in, and you're always going to get a fixed audio, or like depending on how long that audio sequence is, you're going to get a sequence of hidden states from the encoder. But you're not mapping that into a new sequence in like a different domain. All we do is we just add a linear head to do CTC decoding. So actually we can't go into like a different speech domain using this. For that you need an encoder decoder model.
But what you can do is use the MMS checkpoint, convert like speech in one language to text in that language, and then use the width checkpoint, which we will be merging maybe like in a day or two, and then you can like get sort of speech in that, and then you can add another third model in the mix, which would translate the text that you've transcribed to like another language, and then you choose that. So essentially like speech from language 1 to text in language 1, then text in language 1 to text in language 2 via a translation model, and then use the width checkpoint on from MMS to go from text in language 2 to audio in language 2.
Yeah, you could well, if your language was in Whisper as well, so if it's one of the 73 languages in Whisper, then you can just do direct
of course,
translation. So then you go like, let's say you've got language A, which you want to map to language B. So Whisper will do speech to text, A to B, and then you do B text to B speech using the TTS checkpoint. And so you can do this kind of like pipeline approach, but you're going to get error propagation. So if the Whisper model transcribes it wrong, then it's going to say it wrong.
And you lose a lot of information about how everything was pronounced and stuff. So it works. It's not as nice and convenient as an end-to-end solution where everything happens in the same model.
Thank you so much. We already ran out of time for this session, but I think there was a lot of wonderful, interesting questions about all kinds of audio models and applications. It was really interesting to hear your perspectives on different topics. Somebody asked in the chat, what course are we talking about? So this is the link I'm going to drop in the chat in case... Yes, there it is. And with that, if you have any more questions, feel free to join Discord channel. It's, let me just drop that link too. I'll drop it in a second. And we'll be happy to asynchronously pop on in the channel and reply to any more questions. And happy learning. Thank you for joining us. Thank you for staying all the way. Take care.
Thank you, everyone.
Cheers. Bye-bye.
Bye.